Thank you, everyone, for coming to our final presentation of the day. Please go ahead, take a seat, silence your phone. The presentation is Daft and Unity Catalog, a multimodal AI native lakehouse. I will now be handing it over to your presenter, Jay.
Hi. Can everyone hear me okay? That's good? All right. Yeah, great to meet you all. Thanks for coming by. I'll be giving a presentation on Daft and Unity Catalog and kind of extending what we think of today as a lakehouse into the multimodal and AI realm. Like, what does it mean to have a multimodal data lakehouse? And what does it mean to have an AI native lakehouse? We'll be defining that in a little bit. And I'll be showing you all how to kind of couple the things that we know and love, such as Unity Catalog, Delta Lake, Parquet, with an AI multimodal native engine such as Daft. A little bit about me. I am a co-founder at Eventual. That's the company behind Daft. Previously, before this, I used to work at biotech and self-driving at Freenome and Lyft, respectively. I've been building distributed data systems for machine learning and AI for a little bit. So think of shoveling in large amounts of images, LiDAR, genomics data, things that don't really fit in the table, but you still want to use them for your machine learning and AI. And now I'm a maintainer of Daft. That's the query engine and data engine that we've been working on now for about 2 years. I'm excited to show all of you the integrations that we now have with Databricks that can enable you to utilize the entire power of Daft on your current data infrastructure. My goals by the end of this talk is, number one, for everybody in the audience to understand why multimodal data is difficult and why it's different than what we have for tabular data. Number two, I'd love to show you also how the Daft engine makes this much faster and easier than any other data tool out there today. And number three, kind of tie that all back with the Lakehouse architecture that you'll have already in Databricks and just kind of out of the box have that experience with your current Databricks setup. First of all, let's talk about what are multimodal and AI workloads. A lot of people come up to me and say, oh, like AI seems very buzzwordy, right? Everything has AI appended to it today. I think there is a distinction between a more traditional workload and a multimodal workload. So let's talk a little bit about where we came from as an industry. Back in the day, in the 2010s, every company was trying to be a data-driven company, right? And they were making big investments into big data. What does this mean? It actually kind of means that you have raw data. You then run jobs, we call them ETL jobs, extract, transform, and load, and you then build this nice, this like structured set of data that we usually call clean data, or in Databricks terms, you call it the gold tier of your data, right? And then you pipe that into analytics. You use technology such as JDBC, you use dashboarding software like Tableau, Looker, and you plot charts, and this powers business intelligence, right? BI. And this was really what all companies were trying to put investment into in order to be a more data-driven company. A few years after that, machine learning started getting really, really popular, and the use case for data kind of shifted quite a bit. Instead of producing a chart or a graph at the end of this, the end product of a machine learning data flow is usually some sort of model, right? And so in this diagram, you start with raw data. Instead of producing just a normal clean data set, you produce what's called train test split. And so you have your training data set, you have your validation data set, and your test data set. And the goal here is to train a model, right? And so if you notice, the data flow is quite different. And additionally, there's this one last arrow at the bottom, which is the dream of every ML ops, every machine learning company, is that they want to enable this thing called a feedback loop. And the idea is that your model will be outputting data back into your raw data set so that you can then train the model and have it be better and better over time. This really only, I think, happened for a few companies, and the majority of use cases ended up actually being very tabular, if you think about it. Fraud detection is one of those big use cases today, right? Or just general classification problems. And really, machine learning models, I think, overall, started becoming mainly for two main use cases. Number one, classification, and number two, regression, right? Those were the two big use cases that every company was able to leverage using this model, but the training loop and the training cycles would often take days, if not even months sometimes. And it really wasn't until deep learning came around that people started being able to work with multimodal data. Now that you have deep learning, the model, everything doesn't really change except for the model architecture, but because you now have access to things like convolutional neural networks, recurrent neural networks, LSTMs, and in 2017, transformers, you now have the ability to not just work on tabular data sets like number of clicks per user or impressions per user. You now can actually work with things like full text, right? Run an LSTM on it. You can work with images, run a convolutional net on it. And that really enabled multimodal data, but the problem with deep learning was that anyone who wanted to do this, you would have to hire a whole team to manage your GPU clusters, right? You would spin up all these big GPU resources and spend months trying to update your model and trying to get it to work really, really well for a very specific use case. And so really, most companies weren't able to take advantage of this. I was in a self-driving company, and we could do this. But if you weren't in the business of robotics or self-driving, that's extremely difficult to find the right talent that you need to build this kind of a system. And most recently, we now have LLMs, right? And specifically multimodal LLMs. What that means is that there's no training involved anymore. You just kind of plug and play. Well, I'll show a demo later of how crazy this actually is when you apply it on your own data. But you just take an LLM, and now you can apply that on data, whether it's structured or unstructured or multimodal. And you can produce these structured and clean data sets, which themselves may contain some form of unstructured data, like full text, right, generated text. For downstream use cases, you can run this for analytics, you can train your own models, all that. But the interesting thing, too, is that because LLMs are generative in nature, the use cases now extend to classification, regression, and generation. Now you can generate data and have that kind of feedback into your raw data, which is extremely powerful for use cases such as synthetic data generation, never possible before. And so I would argue that the data flow today looks a lot more like this implicitly, even if people don't know that's what they're doing with it. And the tools that we have today need to evolve to this architecture, meaning that this raw data, that's our data lake today. And, you can't really see this, but let me make sure that this code is visible. There we go. It's a little dark. Let me know if you can't see it, but I'll try to explain this as much as possible. Right. So I'm going to be building a data pipeline in Spark. And the data pipeline, I'll just verbally say it because it's too dark to see on the screen. But number one, we're going to download data from, say, 100,000 URLs. Number two, we're going to decode that data into images. The data is just raw bytes now. We're going to decode it as JPEG into images. Number three, we're then going to run it through a model. What does that look like today in Spark, and why is it so hard to do? So the first thing you do in Spark is you read your URLs, and then number one, you repartition. Why do you have to repartition? That's an interesting question, right? Okay, back in the tabular world, this is usually how data flows in a tabular system. You go from say 100 gigabyte data set, and then you usually aggregate your data, right? Data becomes smaller over time in a pipeline. And it becomes very easy to manage this data at the end because it's just a chart, it's just a graph, it's a histogram. It often fits in like 1 megabyte. It's so easy to work with. In a multimodal world, this completely changes, right? I'm getting URLs coming into the system now, and every URL could potentially be pointing to like 10 megabytes of data, who knows? And so throughout the process, your data actually inflates quite a bit, rather than getting smaller because you're running these aggregations and getting it into a form to present in a chart. You're now actually inflating the data, doing things like running models, and when you run a model, the heap memory usage is crazy, right? And Spark has no idea. And so what that means is that when you work with a system like Spark, you have to be very, very careful about how large each chunk of data, or in Spark terms, each partition of data actually is, in order to avoid the issue. If the Spark users in the crowd ever worked with multimodal data, your system's going to explode. It's going to be like out of memory, right? That's because one partition of data inflated to be so large that it just crashed your entire system. Naively batching your multimodal data, just like you do with tabular data, is a very bad idea. 1,000 integers is not in any way equivalent to 1,000 images, right? So that's problem number one. Problem number two, now that we have all the URLs in the system, I'm now going to, you can't see this too easily, but I'm now going to run some Python code, right? I'm going to take these URLs, I'm going to download the data using Python, and then I'm going to decode those bytes using Python again into Python data structures, images. What's the problem with this? Well, in tabular workloads, most of the operations you're ever going to run is included with the data engine. The data engine gives you a way to add numbers together, calculate the mean, hash a number, right? Hashing is just about as complicated as it gets in like a traditional database. In a multimodal AI workload, this is the norm, like not the exception, right? Users are going to come to you with their functionality and their functions, and you're expected to run them. And you're expected to run them without dying and like killing the entire job. That's very, very difficult. And so I make the argument here that like the system looks less like a database and more like a web app. In a web app, you're responsible for running user code. You're responsible for potentially fallible user code. Your user code might, explode and like send you an error. You're supposed to handle that, right? User code might make network calls. That doesn't really happen in database code traditionally. And user code might make unpredictably large heap allocations. It might allocate like 100 gigabytes of memory, and you as an engine have no control over that. And so this is extremely difficult for engines such as more traditional data engines like BigQuery, Trino, Spark that are not really built with this idea in mind that like the user-defined functionality is a first-class citizen of the engine itself. The last thing we're going to do here is we're going to use a model function to run a model, say, on the images in our data, right? Simply expressed as like a UDF in Spark. Why is this challenging? Again, in tabular workloads, the operations are traditionally pretty simple. They just use CPUs, right? You just like stick things into the CPUs, and you have CPU instructions to run addition, hashing, all that fun stuff. In a multimodal AI workload, the operations you run are a lot more complex. They may involve making 1 million parallel calls to OpenAI, right, and hoping that OpenAI doesn't go down or like tell you to slow down. It may involve GPUs. Maybe now you need to use GPUs in your data engine and run a model. And yeah, this means that you have what's called an external dependency. All of a sudden, your data engine can't just do work by itself. It needs to talk to something external, whether that's an external service like OpenAI, whether that's specialized hardware, a device, a GPU device. It needs to talk to that device now. And these operations potentially may be non-idempotent. If you run them more than once, they might not behave the same way. And they have funky APIs and data types, right? The GPUs want you to send in tensors. Spark has no idea what a tensor is, or a token. Like Spark has no idea what a token is either. So it's extremely challenging to work with multimodal data as we know it today. And that's really what we're trying to solve with Daft. You can think of Daft as almost this like new generation Spark that's extremely Pythonic, extremely built for any data modality. So it's simple and reliable data processing, right? Regardless of how big your data is or how small, and also what data modality you're working on. If you're working on integers, numbers, strings, works great. If you're working on HTML, large amounts of text, code, images, video, also works great. That's really the core idea behind what we're doing with Daft. Here's some Daft code. It's very simply a data frame. Looks very similar to what you would see in Spark. You can run, normal data framey stuff. In this case, you can't see the output, but it's basically just calculating the average over a column, very SQL-y. And in fact, you can also run SQL within Daft. And so we built in SQL support because we know that like multimodal support means you also support tabular workloads, meaning you have to do this stuff. And then, yeah, Daft runs locally, and that will be what I will demo in a bit. But when you install Daft, it runs on your single machine, just like Pandas does. And in fact, this is as fast as something like Polars or DuckDB, which are kind of the best-in-class single machine execution engines today, and Daft is built to be just as fast as these engines. Or if your data is huge and you're working with multimodal data, usually the data is spanning, at least hundreds of gigabytes, and you want to spread this out on the cluster to take advantage of the cluster's memory and also network resources. With Daft, all you have to do is kind of point to a cluster, and we use a technology called Ray. And so if you can spin up a Ray cluster, all you have to do is point Daft at it, and we will automatically use the resources on that cluster instead of your local machine. Ray is actually available also on Databricks, and so if you have a Databricks account, just spin up a Ray cluster and point Daft at it, and all of a sudden, you now have distributed computing, which is pretty powerful. And this is Daft working with multimodal data, right? The way it works in Daft is we have custom image types, and so you can see we have an image column. That's not something you see every day, right? But you now have native support for certain multimodal types such as images, tensors, embeddings, and more as we are building them out. And we also baked in a lot of core functionality around multimodal data, such as in this case, what we're doing in this example is downloading data from URLs using a URL download baked-in expression, and then decoding these bytes as images. And internally, Daft is built on a Rust async core library that makes this all super, super fast. To a user, it's almost as if you're using SQL and declaring up front what transformations you want. But under the hood, Daft is doing all sorts of crazy optimizations, native code, Rust, async Rust, to make this all work extremely performantly. Yeah, and so what's the Daft story with Databricks and Unity Catalog, right? So actually, last year in 2024, I don't know if folks in this room were here for the unveil of Unity Catalog. It was pretty dramatic. Like Matei went on stage and he was like, "I'm going to open source this now," and he open sourced Unity Catalog on stage. It was pretty cool. And so we saw that, and then 6 hours after the launch of Unity Catalog, we actually built Unity Catalog support in Daft. And we built this with an open source Python implementation of Unity Catalog, and we donated that back to the Unity Catalog community. And that actually enabled Daft to read tables from Unity Catalog, right? And so this is very basic support. And we could do this so easily because Daft already understands Delta Lake. And under the hood, Unity Catalog tables are actually just Delta Lake. And so we built this in like less than 6 hours, and it was pretty cool. And what that looks like is this. You would just create a Unity Catalog instance, attach it to Daft attached catalog, and then now you can read any table in your Unity Catalog just by specifying the table name, and Daft will find it by making API calls to Unity Catalog. This is really cool because prior to this, there actually wasn't any real way of reading a Databricks table if you weren't inside of Databricks. You can do this anywhere now. You can do this on your laptop. You can do this on an EC2 machine. You could do this from a Raspberry Pi. You don't have to be in Databricks anymore to read your Databricks tables if you have an engine like Daft that understands how to interact with Unity Catalog. Now, this year, we did a second tier of integrations because Daft is a multimodal engine. We want to integrate natively with Unity Catalog volumes, right? Volumes are really the story for storing multimodal data. And what that looks like is something like this, where your URLs, all you have to do is prepend your URL with dbfs:/. If you're a Databricks user, this is a very familiar pattern. It just means like hit my volume, right? And Daft now understands this URL and can map that to the appropriate Unity Catalog volume and find your data for you and download it. Again, you don't have to be in Databricks to do this. All you have to do is have Unity Catalog, and you could be running this on a Raspberry Pi. And this would work, right? Because we're not actually using the Databricks file system. We're actually hitting the Unity Catalog instance and then going outside of the entire ecosystem to fetch your data. So what this enables is, I would argue, a truly multimodal data lakehouse. Because now you can read both the tables and the volumes, which means both your tabular data is covered and also your multimodal unstructured data is covered. And so what Unity Catalog really gives you is unified governance over your data. Daft provides you still with the tabular data processing that you need with SQL and data frame APIs, but now all of a sudden you have multimodal data workloads, right? You can read from Unity Catalog the volumes into rich types such as images and tensors, convert them to PyTorch, and that's something that we will now demo. Let's take a quick look at a live demo. Fingers crossed, everything works. But we will see that in this live demo, we're going to be running, Daft against Unity Catalog. Let me increase the size of my screen. Collapse this. Yeah, so note that this demo right now is actually just running on my laptop. I'm not even in Databricks, right? I just have a Databricks account somewhere, and I got some credentials, and that's it. There's no other credentials, just Unity Catalog credentials and my laptop. And so I would argue that in 2025, the Lakehouse is finally truly open. You can access it from anywhere. Databricks has made good on its promise to make this open, which is amazing. So what this demo looks like, just a quick diagram, is, let me zoom out a little bit. So this is the Lakehouse architecture, right? We have raw storage, which is Amazon S3. And then we have Databricks, which is hosting Unity Catalog. Databricks itself doesn't store the data. They just basically hold pointers to data in S3. And then you have your compute engine. So you have your raw data, you have your catalog, and then the compute engine, which is Daft. And what Daft does in this demo is it's asking Unity Catalog for credentials. It's asking it for pointers to the data, right? And all Unity Catalog is doing is granting us permission to read this data, and then it's going directly to S3 for your actual data access, which means that, like, yeah, you're actually not going through any Databricks infrastructure to pull that data out, except to get permissions to do this, which is really powerful, as we'll see in a bit. All right, let's get started with the demo. So first of all, I've already gone ahead to install Daft, and you can import Daft very easily by just import Daft, just like that. I have a bunch of setup code, and then now we will attach Unity Catalog to our current session. And so I'm grabbing a Unity Catalog endpoint, which is actually my Databricks account, like URL, and I'm grabbing a token, which I've hidden from you because that's secret. You can't see that. And now I'm just attaching this instance of Unity Catalog to Daft, and so Daft now has access to all of my Unity Catalog, which is amazing. Because what we can do now is we can load these volumes and tables by name, right? So here's an example of a volume. This is a very new API in Daft that we've built to enable interactions with volumes, but now I can just reference a volume by name. That's just, my catalog is called JTestUnity. The schema is default, and then the volume name is test managed volume. And voila, we now have access to this volume. And we can actually inspect it, like, what is a Unity volume? In fact, a Unity volume just holds a pointer to S3, this like super scary, convoluted looking S3 path, right? That's a Unity volume. And all it's doing is vending credentials over that volume for me. And so now that I have access to this Unity Catalog volume, I can now do all the work that I need to access data within the S3 bucket without your user or you, as you're using this system, even knowing that S3 is in the picture. We'll see that in a bit. So first thing I'm going to do, I'm going to read a table now from Unity Catalog. So all you do is you do daft.read table. Tell it what table you're trying to read. This is the table identifier in Unity. And voila, this is my table. For this demo, we will be using the Lion dataset. Have folks heard of the Lion dataset? Okay, one person, two people. Lion is an image dataset. It was very popular, I think, a couple of years ago, and still is. Basically what they did was they crawled the entire internet for images. And so what you'll see is that on the left, there are all these public URLs. It's like random URLs from the public internet. And in fact, they also captioned it. And so you'll see a caption column, right? This image represents some sort of bedroom. This one is some sort of memorabilia, high-waist sleeveless, mini soft jeans, and then a public URL. The problem with Lion is that it's very dirty. A lot of these URLs are down now because, these are just public URLs, right? And so what I did is I used Daft to curate this data set and get rid of any broken URLs. And additionally, what I did was I ingested all the data into Unity Catalog volumes. So here we have a new column that I added to the Lion dataset that I ingested the images into a volume. And so it's a volume because the URL starts with dbfs:/, right? This is just like inside of my Databricks account somewhere. The volume name is this one, JTestUnity default test managed volume. And if that looks familiar, it's because it's the volume that I accessed from before. So my goal now is like, cool, I have this kind of table of metadata. Like, how do I actually retrieve the images and do some work on it, right? So let's do that really easily. All we have to do, I guess also to prove to you that I'm not in Databricks, I'm going to try to open one of those URLs, the dbfs URLs. And as expected, it's going to throw an error, right? Because again, I'm not in Databricks. And so this dbfs URL doesn't mean anything to my Python process right now, unless you use Daft, because Daft understands what dbfs:/ means, and it will attempt to map that to Unity Catalog. So let's run a very simple Daft operation, which is, Daft, please create a new column called image. We will now run this URL download operation on the Unity volume URL column, which will download bytes, and then we'll take those bytes and decode them into an image column. And there we go. Notice how fast that ran too, right? Like Daft under the hood does a lot of crazy async IO stuff to make this all work. But yeah, these are like, full res images being pulled down from your Unity Catalog volume. And now we have a new column called image that is, if you notice, of image type. It's a native Daft column type. And that was all in like 3 lines of code, right? Actually, yeah, like 3 lines of code, which is quite amazing. All right, so that was the big unlock, I think. Now you have all your data kind of behind Unity Catalog, both the tables and the volume, and then you have S3 for the raw storage and Daft as your engine. And that's, if you notice, a Lakehouse. Next thing we do, let's actually make this useful. Let's run some LLMs, right? I built a very simple LLM here, LLM prompt. Basically, I'm like, those captions that we saw, they were pretty bad. I don't know who did them, but they're horrible. I wanted the LLM to generate good captions, right? Maybe the use case here is I want to train a model downstream, and I want it to make better captions. And also, I want the LLM to score these captions for me, like get rid of the really horrible ones. Like that's just low quality data. I don't want that in my data set. And so I built a very simple prompt here, like, hey, here's how you define caption quality. Like I want captions that make grammatical and logical sense. I want this to be I want captions to capture like semantically important focal points, not just describe what's in the image, but capture important context around the image. This is important because we'll see the LLM actually doing this later. And I've hidden a bunch of code here, but this is where I defined my UDF for Daft, and that UDF is called score caption. And so all I have to do now is I just run that UDF on top of my caption column and my image column, and I'm going to pull out a couple of new columns called caption similarity, caption quality. I want a new clean caption, and then I want the reason as to why the LLM made that choice. And let's show the first couple of results. This should run pretty fast. Give it a couple of seconds. And so under the hood, it's like fanning out, like requests to OpenAI. There we go. Here are some new results. So here is the original caption of this one. This is a bedroom, right? Home interior storage for kids' bedroom design. And the clean caption says minimal bedroom interior with extensive wooden storage and large wooden bed. The caption quality was only 0.7. And the reason was because it does not mention that it may be designed for kids. And so if you notice in the original caption, it says like for kids. But if you zoom into the image, it's like not really for kids. And so that's why the model decided to score it that way. And so this is really useful, right? Because you can kind of use this unstructured data processing or multimodal data processing to really clean up your data sets, as I mentioned, and harness the power of LLMs within your data processing. Let's take a look at another fun one. How about this one? This one has a really low score, 0.35. That's kind of sad. Why is that? If you look at this, it's some sort of album cover, but the caption is just Alhurt Boston Pops Vinyl 12 used, right? And the reason the LLM gave such a low score was it's saying that, hey, this caption lacks clarity, adds extra text like Vinyl 12 used, which distracts from the main content. It doesn't really tell you that this is an album cover. And if you notice, the clean caption says album cover for Alhurt and the Boston Pops, conducted by Arthur Fuetler or whatever. So it's much better, right? It's a much cleaner data set that you can now use for downstream consumption. Beautiful. So that was so easy in Daft. You just kind of ran this operation, run an LLM on it. Let's go ahead now and take out the image, because images are very expensive to store in a table, right? And we already have a URL, so no need to store the image. And I'm just going to write the data set back out. Let me delete my previous runs. And let's write the data set back out to essentially our data lake, right? So I'm going to write this out as Parquet, as a new Parquet file in this clean captions column. So it's going to run way more than what we just ran, so a much larger data set. And it's going to hit OpenAI, run all the inference, and store all of our, inference results and all the scoring made by the model. The scoring by the model, interestingly, is a lot better than the one provided by Lion, because Lion, if you notice, all the similarity scores are hovering around 0.35. It doesn't really score very well, but the model is very opinionated. It's like, oh yeah, this one sucks, It's 0.35, or this one's really good. It's 0.8. So there we go. It wrote the data out. And note that all the operations that I just ran here ran on my local machine. But if you had way more data and the need to download a lot of these images, what you want to do is actually run this on a cluster. And that's just as simple as setting Daft's context set run array, and now you're pointing at a cluster instead, and we will use cluster resources to run all the operations. Okay, now that we have this clean data set, let's go ahead and load this data into PyTorch for training, right? That's a very common next step. You're like, let me pull this data in and run this through a model or like in PyTorch. So how you can do that, we do read parquet, and then we just do the same thing again. We'll just download the data again from the Unity volume URLs to visualize this and to pipe it into PyTorch. And I'm going to sort this by descending caption quality because I thought that'd be fun to show you the worst captions. So here we have some pretty bad scores, 0.2. Let's see what this is. Oak Furniture Land was the original caption. It's basically saying that like this is a logo, but Oak Furniture Land gives you no information about that. And so now the LLM says this is an Oak Furniture Land logo with a green oak leaf design, which is like way better, right? But the original caption quality was like 0.2. So this is great, and I want to just like get rid of these bad caption quality rows. And so what I can do is I just specify, hey, given my data set, I want to filter out all rows where caption quality is not at least 0.5, just get rid of them. They're probably like low quality, high noise data. This is how you enhance the data set quality for machine learning and AI in general. And yeah, now I'll convert it to a PyTorch data set. And now you are in PyTorch land, and this is extremely fast. Daft will run this kind of in a pipeline fashion and feed you data just by iterating on it, and now you get all of your data here, along with the metadata, right? That's like reason, caption, and this is the stuff that you will use to feed into your GPUs and your model training downstream. That was the end-to-end use case, right? Now you have a multimodal data lake, and you're just kind of loading from it natively into Python and PyTorch. Notice how there was like no cluster involved. You didn't need to spin up the JVM, some like Spark cluster. Notice I didn't install any jars. Like no, like it's all like one notebook, one install, pip install Daft, and you're good to go. Pretty amazing. All right, let's continue with the rest of the presentation to round up. So this is your multimodal data lakehouse. You have Daft, the engine, on top, and then you have Unity Catalog, the catalog layer, and then below that, you have the raw data storage, S3. And it's like super simple. These are all the interactions that happen within the lakehouse, but it's such a simple architecture. How does Daft do it? So under the hood, Daft actually does what's called dynamic streaming execution. Remember how I told you before that Spark really struggles with like batching of your data, and it's just like static batching, and you have to like make sure that your batches are small enough that it doesn't explode memory. Daft has a very sophisticated dynamic streaming execution engine. So in this use case, the batches of data are represented by the size of these pink boxes. Notice how when you are reading from your tables, it's a small like batch. When you're joining the data, it's a pretty big batch. But then as soon as we get to the URL download, the image decode, Daft can recognize that this is like a very multimodal operation, and therefore it should use small batches. Because when you download images from a URL, it's going to like expand your data by quite a bit. And so it's going to stream the data through in much smaller batches to keep your memory usage stable and not kind of materialize it every step of the way. And this is what makes Daft really powerful and not go out of memory when working with multimodal data. The second thing is when working with user-provided code, right? When the user gives us code, Daft actually doesn't use any external JVM processes like Spark. And so what that means is that everything happens in one process. You don't get Py4j errors or like gateway errors or any of that anymore. It's all one process. There's no communication between processes. And we have very nice zero-copy integrations with PyArrow. And so if you have any sort of arrow-based system, Daft actually integrates super, super nicely with them. You can kind of move data back and forth really easily. That includes systems like NumPy, PyTorch, and that's what makes Daft really powerful when working with the Python ecosystem. And lastly, Daft has I didn't show this, but Daft actually has a really good resource-aware scheduling concept, right? Where you can actually tell Daft, hey, I want to run this operation, but I need a GPU to run it. And Daft will find the GPU for you. It will throw you an error if your GPU doesn't exist. But if you tell it, I need one GPU to run this thing, it will schedule your work with that in mind. And so on the right here, I have an example where in addition to traditional database concepts like projections, you have special types of projections like actor pool projects, we call them, which is actually, we will find the GPUs and make sure that each GPU has one process that's running on it. So you no longer have to wrangle with Spark and try to get it to use your GPUs, right? You just tell Daft, hey, here are my resource requirements, and Daft will handle all of the scheduling for you, including things like GPUs. It's also aware, for example, if you say like URL download, it knows that URL download is very high network utilization, and it will attempt to pipeline that with your CPU utilization, which is extremely powerful in a multimodal setting. So here are some of the roadmap items that we have. I'm gonna breeze through these so that we can get to Q&A. But yeah, we're gonna be trying to integrate also with Unity Catalog functions and models. I think a pretty natural transition. Tighter Databricks integrations. You should be able to work with Databricks regardless of where you are. That's a key kind of commitment that we have. Like, you should be able to do it from EC2 or your laptop, Raspberry Pi. Like, you should be able to do that. And then tighter GPU integrations. That's a lot of people, what they want to do is take data from, say, Iceberg, Delta Lake, and put it into a GPU so that they can then do work on it. And then, yeah, we actually have a early access kind of managed service for Daft. Like, we'll figure out what cluster resources are necessary to run your workload. And yeah, we'll help you run your multimodal data, PDFs, images, videos, HTML, regardless of how big it is, right? Dump us a 100 terabyte thing and we'll be able to run it all the same. That's really the goal with what we're building here. And yes, we're hiring. So if anyone's interested in working on this kind of stuff, please get in touch across engine roles, product roles. If you're interested in like pre-training AI, if you have experience there, we'd love to chat. And if you're working on storage engines and cloud storage, that's also really powerful. And yeah, send us an email. I think that was it. We'd love to take questions now. But yeah, pip install Daft, give us a try, give us a star. Yeah, happy to take questions.